What if the universe we see is only a small fraction of what is really there? And what if vast layers of reality have always surrounded every galaxy, every filament, and every dark region of space while remaining almost completely hidden? Now, the Euclid mission is beginning to map that unseen cosmos in extraordinary detail, and its first clues suggest that what looks empty may not be empty at all. If this kind of deep space mystery is fascinating, please like the video, subscribe to the channel, and stay with the journey. At the largest scale that human instruments can examine, the universe appears as a field of light set against immense darkness. The eye that looks upward from Earth sees stars, faint bands, and scattered points. A telescope extends that sight and reveals that most of galaxies, each one holding enormous populations of stars mixed with gas, dust, planets, stellar remnants, and thin clouds of hotter material. When astronomers describe the visible universe, they mean this realm of detectable light, light that reaches a mirror, a sensor, or a photographic plate after travelling across space for very long spans of time. It is the part that can be counted first, because it shines, glows, reflects, or absorbs in ways that make its presence known. Even in this visible layer, the scale is difficult to hold in the mind for long. Galaxies do not lie close together like stones on a path. They are separated by distances so vast that ordinary language strains to keep its balance. Between one bright system and the next, there may be expanses of near emptiness, where only a few wandering stars, clouds of gas, or sparse dwarf galaxies drift through the dark. Yet the overall sky is not random. When large surveys gather the light from many millions of galaxies, patterns begin to emerge, clumps, arcs, chains, and open regions spread across the map. The visible universe starts to resemble a grand arrangement rather than a mere scattering of lights. It becomes a structure. For much of human history, the shining part of the cosmos seems sufficient. The sun dominates the day, the moon and stars shape the night, and the Milky Way appears as a pale river across darkness. Modern astronomy changes that proportion. It shows that the bright surfaces and glowing interiors of stars are only one way matter announces itself. It also shows that even when all visible stars and galaxies are counted with care, the total does not fully explain how the cosmos behaves on its largest scales. The visible share is real, rich, and measurable, but it is not the whole account. It is more like the illuminated skin of a deeper structure. This is the starting point for Euclid. The mission does not begin by assuming that space is empty wherever nothing shines. Instead, it treats the visible sky as a record that may carry the imprint of far more than it directly reveals. Euclid is an ESA space telescope designed to examine the large-scale structure of the universe across a vast area of sky and across a long stretch of cosmic time. It surveys regions beyond the crowded foreground of the Milky Way, where the light from distant galaxies can be measured in enormous numbers. Its purpose is not simply to gather beautiful images, though it does that with great clarity. Its deeper purpose is to turn the visible sky into a precise map of cosmic arrangement. That task rests on a simple but profound scientific habit. Before explanation comes inventory. Astronomers begin with the contents of the light itself, with the apparent number of galaxies, their estimated distances, their distribution, and the way their shapes, colours, and brightness vary across the sky. In this outermost region of the subject, the work remains close to direct observation. Light arrives. Instruments record it. The sky is divided into measurable pieces. The ancient human act of looking upward becomes, in modern form, a census on the scale of the cosmos. A census of this kind reveals something quietly unsettling. Ordinary matter, the kind that forms stars, planets, gas clouds, dust grains, living bodies, and every familiar solid, liquid, and atmosphere, makes up only a small fraction of the total contents of the universe. Observations from many branches of cosmology point to a picture in which the greater part is not visible in the usual sense. One component is called dark matter, meaning matter that does not shine yet seems to exert gravity. Another is called dark energy, a name given to the still uncertain cause of the observed accelerated expansion of the universe. Together they dominate the cosmic budget. The bright matter that fills telescopes with colour and structure is the minority share. In this broadest opening layer, that fact matters less as an abstract number than as a change in perspective. The sky that appears full is, in physical terms, only partly disclosed. A galaxy glows because stars burn within it, because gas is heated, because dust interacts with radiation, because matter in ordinary atomic form leaves visible traces, but the total setting in which that galaxy exists is not exhausted by what it emits. The familiar luminous cosmos becomes something like a surface pattern laid over a much larger hidden arrangement. Nothing in this statement implies complete knowledge of the hidden part. On the contrary, it marks the boundary between what is seen directly and what must be inferred from wider evidence. Euclid enters this boundary with unusual breadth. Over years of observations, it records billions of galaxies and reaches back across roughly 10 billion years of cosmic history. That depth matters because distance in astronomy is also time. Light from very remote galaxies begins its journey long before Earth takes its present form, and when it arrives it carries an old image of the cosmos. A sky survey is therefore not only a map spread outward in space, it is also a layered record of the universe at different ages. Nearer galaxies show a more recent state. Farther galaxies show an earlier one. In the visible sky, space and history are folded together. Seen from this outermost vantage, the title of a missing universe does not mean that a literal piece has broken away and vanished into nothing. It means that the cosmic account appears incomplete when judged by light alone. Something important does not show itself in the straightforward way stars and galaxies do. The missing part is not missing from reality. It is missing from direct view, missing from ordinary expectation, and missing from any simple picture in which the shining universe is assumed to be the whole. Euclid begins from that plain recognition. The visible cosmos is rich beyond ordinary comprehension, yet it may still be only the exposed fraction of a much larger order. A survey of the universe cannot begin by pointing anywhere at random. Even before the first distant galaxy is measured, the sky must be divided into useful and less useful regions. This is the next layer inward from the broad fact that the visible cosmos is only a partial account. Once astronomers accept that the whole cannot be understood from a few isolated views, they must decide where to look steadily, where to return often of attention. Euclid enters the sky in this deliberate way. It does not attempt to observe every direction equally. It selects windows. These windows are chosen because the sky is not equally transparent to a survey that wants to look far beyond the Milky Way. The bright band of the Milky Way itself stretches across the sky as a crowded foreground. In that band lie enormous numbers of nearby stars, along with gas and dust that scatter, absorb, and complicate the incoming light from far more distant galaxies. For an astronomer interested in the large extragalactic scene, this region is not useless, but it is difficult ground. A space telescope designed for cosmology gains more by looking away from this crowded lane, toward areas where the local foreground thins and the distant universe can be recorded with less confusion. Another layer of interference comes not from the galaxy, but from the solar system. Fine dust spread through the inner planetary system reflects sunlight and produces a soft, diffuse glow known as zodiacal light. It is not dramatic to the eye, yet to a precision survey it matters. A faint veil across a large field can reduce the contrast needed to measure dim structures and distant galaxies with the required consistency. So Euclid avoids not only the densest stellar zones of the Milky Way, but also regions where this diffuse solar system light becomes a stronger contaminant. The result is a carefully shaped observing footprint, not a simple circle and not a casual patchwork, but a selected domain across the extragalactic sky. This choice already says something important about the title of a missing universe. The apparent absence of matter is never judged from an unrestricted glance. It is judged through observations made under conditions that are quiet enough for the distant background to emerge. In this sense, the search begins with subtraction. Foregrounds are reduced, bright local clutter is set aside, dust, glare, and crowding are minimized as much as possible. What remains is not emptiness, but a cleaner stage on which the distant cosmos can be counted. Most of Euclid's work belongs to a wide survey. This is the broad cartographic effort, stretching across more than 1/3 of the extragalactic sky outside the Milky Way. It is large by design because cosmic patterns do not reveal themselves well in small, isolated frames. A narrow image may contain beautiful galaxies, but it cannot easily show how one region relates to another across great spans. A wide survey creates continuity. It allows the distant sky to be sampled over huge areas, so that local peculiarities do not dominate the overall picture. In this layer of the story, breadth is not a luxury, it is a requirement. Yet Euclid does not rely on breadth alone. Alongside the wide survey, it devotes a smaller share of observing time to 3 selected deep fields. These are not broad windows opened once and left behind. They are regions chosen for repeated visits. The same areas are observed again and again so that faint sources accumulate in the data and the map grows steadily richer. If the wide survey provides geographic reach, the deep fields provide persistence. They are fixed places where the telescope lingers. The placement of these deep fields is itself revealing. All 3 lie in parts of the sky that appear relatively clear between the clouded and crowded features of the foreground maps. One of them, Deep Field North, lies very close to the north ecliptic pole in the constellation Draco. Its position allows especially frequent coverage through the year. That makes it a practical anchor for repeated observations. It also overlaps with an area already examined deeply by earlier infrared work, which gives Euclid's survey a useful connection to previous astronomical records. The field is not chosen simply because it is empty. It is chosen because its emptiness is scientifically productive. A second field, Deep Field Fornax, lies in the southern constellation Fornax. It includes within its borders the much smaller Chandra Deep Field South, a region studied for many years by major observatories working in X-ray, optical, infrared, and from the ground. This makes Fornax another kind of window, not a blank page, but a page with earlier notes already written in the margins. Euclid adds scale and uniformity to a place that has already been examined in great detail by other instruments. The field becomes part of a longer scientific continuity. The third, Deep Field South, lies in horologium and is the largest of the three. Unlike Fornax, it is not defined by long prior use as a famous deep survey site. Its importance comes partly from that relative openness. It offers the chance to examine a broad, deep region without leaning so heavily on an already familiar patch of sky. In this sense, it balances the survey strategy. One deep field gains strength from seasonal accessibility, another from overlap with extensive earlier observations, and another from the promise of discovery in a less charted region. Together they form a small set of fixed observational homes within the much larger survey. By March of 2025, Euclid's first public survey release already provides a preview of what this arrangement can do. In just one pass across each deep field, millions of galaxies appear. The combined preview spans more than 60 square degrees, an area vastly larger than the tiny pencil beam studies that once defined the phrase deep field in popular imagination. Euclid's depth is therefore paired with scale. It does not stare into a narrow hole in the sky alone. It builds large mosaics, wide enough for structure and rich enough for accumulation. The deep fields are deep not because they are small and isolated, but because they are returned to repeatedly over the mission. In this second region of the subject, nothing mysterious has to be inserted by hand. The method itself carries the meaning. A hidden cosmos can only be approached through disciplined selection of sky, clean lines of sight, repeated measurement, and careful separation of foreground from background. Euclid's windows are the practical expression of that discipline. Before the mission can ask what is missing from the visible account of the universe, it must first decide where the visible account can be read most clearly. The survey begins there, in those quiet openings where the nearer clutter thins and the distant sky has room to speak. The sky that Euclid studies is not only spread across great distances, it is spread across great ages. This becomes clear as soon as attention shifts from where the telescope looks to what actually arrives from those distant regions. What reaches the instrument is not matter itself, not a direct sample of a galaxy carried through space, but light. That light begins as radiation released by stars, gas, dust, and energetic processes inside galaxies. It then travels outward across expanding space for immense spans of time before it is finally recorded. In this sense, every observation is delayed. The telescope never sees a galaxy as it is at the moment of observation. It sees the galaxy as it is when the light begins its journey. This delay is not a flaw in astronomy. It is the condition that makes cosmic history visible. Nearby objects are seen in a relatively recent state because their light crosses shorter distances. More distant objects are seen in earlier states because their light takes far longer to arrive. A survey that reaches deeply into space therefore reaches deeply into time as well. The farther Euclid looks, the older the image becomes. The sky turns into a layered archive in which distance and age are joined together, at the broadest human scale. Daily life gives little preparation for this fact. Light seems immediate. A lamp glows when it is switched on. The sun lights a morning sky. A room brightens at once, but over cosmic distances. Even light moves through intervals so vast that the visible universe becomes a record of former conditions. The night sky is not a single moment spread overhead. It is a mixture of moments. Some lights are comparatively recent. Some belong to epochs long before Earth takes its present form. Astronomy works by accepting this mixture and learning to read it. Euclid is built for that reading. It observes in visible light and near-infrared, the part of the spectrum just beyond human vision at longer wavelengths. This matters because light from very distant galaxies does not remain unchanged during its journey. As the universe expands, the wavelength of that light is stretched. Astronomers call this redshift, meaning that light is shifted toward longer wavelengths, toward the redder end of the spectrum and beyond it. A galaxy that emits much of its light in visible bands can therefore appear moved toward the infrared by the time that radiation reaches a detector. To observe the remote universe well, a telescope must be able to follow that shifted light. In this third region of the subject, the hidden quality of the cosmos begins to take on a gentler meaning. Some things are not hidden because they are absent. They are hidden because their light arrives altered, weakened, and delayed. The farther a galaxy lies, the fainter it usually appears, and the older the message becomes. Space does not simply separate observer and source. It transforms the signal by stretching it across time and wavelength. What Euclid receives is therefore not just distant light, but light that carries the marks of travel. That travel is extraordinarily long and quiet. Once photons leave a distant galaxy, they move across intergalactic space through regions that are, on average, extremely thin. They are not gliding through a crowd of obstacles. Most of the cosmos is sparse. Even so, the journey is not simple in an observational sense. With increasing distance, brightness falls. Details blur into smaller apparent shapes. The radiation shifts toward longer wavelengths. Signals from many epochs gather into the same field of view. Euclid must therefore combine sensitivity, stability, and breadth, not because the light is dramatic, but because it is subtle. A distant galaxy may contain billions of stars, yet from far enough away it becomes a faint patch of structure, its internal parts too small or too dim to stand apart clearly. Euclid does not need every galaxy to appear as a richly detailed portrait. For much of its science, it needs the light to be measured consistently across immense numbers of sources. That consistency depends on stable optics and well-calibrated detectors. In visible light, the VIS instrument records sharp galaxy shapes across wide fields. In near-infrared, the NISP instrument helps extend the reach of the survey toward more strongly redshifted sources and provides information that helps estimate how far away many galaxies are. In this layer of the story, the telescope acts less like a collector of isolated spectacles and more like a disciplined reader of ancient signals. The signal itself is modest. A distant galaxy does not announce its age openly. Its light must be interpreted through colour, brightness, and the degree to which known spectral features are shifted from their usual positions. That is why astronomers treat light not merely as illumination but as evidence. A change in colour can reflect stellar populations, dust, or cosmic stretching. Apparent faintness can reflect true smallness, great distance, or both together. Nothing is understood from a glance alone. Yet when billions of sources are measured by the same system, patterns emerge that are stronger than any one object's ambiguity. The great value of Euclid's long look into the sky lies here. It can observe galaxies from relatively recent cosmic times and others from much earlier ones within one coordinated survey. This means the telescope does not simply assemble a flat celestial picture, it assembles a time-layered one. The visible universe becomes a sequence of older and younger scenes mixed across the detector. Nearer galaxies show structures that have had more time to grow and change. Farther galaxies show the cosmos in less mature states. The survey therefore becomes a way of comparing different ages without leaving the same general act of observation. By receiving old light and newer light together, Euclid turns the sky into a historical field. This historical field is especially important because the mission aims to trace the large-scale development of the universe over roughly the last 10 billion years. That span covers much of the era in which galaxies, clusters, and the broad cosmic web take the form seen in the more local universe. It also covers the period during which the expansion of the cosmos becomes a central observational problem. Yet within the boundaries of this section, the emphasis remains on the arrival of the light itself, before any structure is counted, before any hidden mass is inferred. The first fact is simply that the universe sends its path toward the telescope continuously. So the distant sky is not silent darkness interrupted by isolated lights. It is an old and ongoing transmission. Each faint galaxy is a source whose radiation has been crossing space while stars are born and die, while galaxies merge and separate, while the fabric of the cosmos continues to expand. Euclid receives this layered stream and records it with enough precision that age can be read from distance, and distance from altered light. In that steady arrival, the visible universe becomes more than scenery. It becomes memory made observable. Once the light from distant galaxies has crossed space and entered the telescope, it must be turned into something more durable than a fleeting signal. This is the next inward layer of the subject. The sky has already been narrowed to carefully chosen survey windows, and the arriving light has already been understood as a record of different cosmic ages. Now that light becomes a census. The task is no longer simply to receive ancient radiation, but to sort it into measured entries that can be compared across the whole survey. Euclid does this by transforming countless faint sources into a common form of astronomical record. A census begins with recognition. The detector gathers light as a field of brightness spread across many pixels. Within that field lie stars in the foreground, galaxies at many distances, occasional artifacts produced by cosmic rays or instrumental effects, and faint structures near the edge of detection. The first practical act is to identify which patches of light correspond to real celestial objects. This sounds simple at first, but in a deep, wide survey it becomes delicate work. A galaxy may appear large and clear in one case, or small and nearly star-like in another. Two neighbouring sources may overlap slightly. Diffuse light from bright objects may affect the measured edges of fainter ones. The census therefore begins with careful separation. Once a source is recognized, its position on the sky is recorded. This may seem like the most ordinary part of the exercise, yet it is essential. A galaxy catalogue is not just a collection of images. It is a map in coordinate form. Each object is placed at a precise location so that it can be compared with nearby objects, matched with other surveys, and revisited in later observations. On a human scale, a map pin simply marks a place. On a cosmological scale, many millions or billions of such pins become the foundation for studying structure. In this section, however, the emphasis remains on the making of the pins themselves. Brightness comes next. Euclid measures how much light a source contributes in its observing bands. This helps distinguish faint galaxies from brighter ones, and provides one of the basic descriptors for every entry in the catalogue. Brightness alone does not tell a full story. A nearby small galaxy may appear brighter than a very distant large one. Dust can alter the observed light. Stellar populations inside galaxies can give different colour balances. But the measured brightness remains one of the most direct facts the telescope can collect. It is part of the raw inventory of the visible sky. Shape is equally important. A galaxy is not only a point and not only a brightness value, it has an extent, an outline, and a distribution of light across its visible form. Some appear smooth and rounded, some are elongated, some show spiral structure or irregular clumps. At the distances relevant to Euclid, many are too small or faint for detailed visual classification in the familiar sense, yet their overall form can still be measured. The apparent width, orientation, and degree of elongation all enter the catalogue. These shape measurements are only as good as the clarity of the instrument and the stability of its imaging, because the telescope itself affects how any source appears. For that reason, the census includes not only the galaxies but also a careful understanding of the imaging system. Colour also enters the record. In astronomy, colour means the relative brightness of a source in different bands of light. This is not merely decorative language. It helps indicate the nature of the light-emitting population within a galaxy and, very importantly, how far its light has been shifted during its long travel through expanding space. Euclid's visible and near-infrared observations provide a way to estimate this shift for large numbers of galaxies. These estimates are not the same as the most exact spectroscopic distances gathered one object at a time with a full spread of wavelength detail. Instead, they are broad survey tools built to work at immense scale. They allow the census to move beyond a flat sky map and toward a layered record in distance. Distance estimation changes the meaning of the catalogue. A list of positions on the sky alone is still something like a painted ceiling, all objects projected onto one surface. Once approximate distances are added, the catalogue begins to recover depth. Galaxies that appear near one another in angle may in fact lie very far apart along the line of sight. Others that seem scattered may belong to a similar cosmic epoch. The survey does not immediately become a perfect three-dimensional map, but it acquires thickness. The sky stops being a flat arrangement of lights and begins to resemble a volume filled with sources at many depths. This transformation depends on uniformity. A census is scientifically powerful only when one entry can be trusted to mean the same kind of thing as another. If one part of the survey measures brightness slightly differently from another, or if shape estimates drift because of changing image quality, the catalogue becomes patchy in a harmful way. Euclid is therefore built not only to observe many galaxies, but to observe them under tightly controlled and well-calibrated conditions. Flatness of detector response, stability of pointing, knowledge of the instrument's optical blur, and consistent data processing all help ensure that one region of sky can be compared fairly with another. The invisible labour of calibration is part of the census, even though it is not itself a celestial object. At large scale, this work produces numbers so vast that the ordinary meaning of counting begins to change. No astronomer reads such a catalogue line by line in the way a clerk might once read names from a ledger. The census becomes a data structure of immense size, containing measurements for millions and eventually billions of galaxies. Yet its purpose remains close to the oldest meaning of a census. It is still an attempt to know what is there, where it is, and in what basic form it appears. The difference is one of scale and depth. Euclid does not count households, villages, or cities. It counts distant systems of stars across much of the observable cosmos. In this region of the story, the idea of a missing universe becomes more disciplined. The claim does not arise from impression. It does not arise because the night seems dark or because a few unusual objects appear puzzling. It arises only after the visible contents are gathered into a measured inventory and treated as a coherent population. Before any larger interpretation is attempted, the luminous part of the cosmos must first be described in common terms. Position, brightness, shape, colour, and estimated distance form that common language. So Euclid's census is an act of conversion. Ancient light becomes structured information. Scattered galaxies become entries in an ordered survey. The visible sky, once experienced as a vast field of separate gleams, becomes a disciplined catalogue from which deeper understanding can gradually be drawn. Nothing hidden has yet been mapped in this section. Nothing unseen has yet been inferred. The work remains with what can be measured directly from the incoming light, but already the visible universe has changed its character. It is no longer merely looked at, it is counted. When the census of galaxies grows large enough, the visible universe stops resembling a random sprinkling of isolated systems. A new layer comes into view, not through any single object, but through the arrangement of many objects together. This is the region of pattern. Positions that seem merely scattered in smaller samples begin to reveal long strands, broad walls, branching connections, and wide spaces in between. The sky, once turned into a catalogue, now begins to show its architecture. Euclid enters this stage by taking the immense list of measured galaxies and allowing their collective distribution to speak. At first glance, any map of galaxies can appear crowded in some places and sparse in others because of perspective, distance, or incomplete coverage. A few bright examples are never enough to show the deeper order. The large-scale pattern emerges only when the survey becomes both wide and deep, when millions of galaxies are placed across a common frame and their approximate distances give the map thickness. Then the visible cosmos begins to display what astronomers often call the cosmic web, a term that means the network-like arrangement of matter on the largest known scales. It is called a web because galaxies do not fill space evenly. They gather along elongated structures and junctions, leaving immense lower density regions between them. This pattern is not decorative. It is the visible expression of how structure develops in an expanding universe. Over long cosmic time, matter does not remain perfectly smooth. Slight early differences in density grow under gravity. Regions that begin only a little denser than average gradually attract more material. Regions that begin a little thinner lose relative prominence. The result is not a simple collapse into one central mass. Because the universe is expanding as this process unfolds, and because the initial irregularities are spread across space in many directions and scales, what forms instead is a hierarchy of connected structure. Matter gathers into extended filaments and leaves behind regions of relative emptiness. The web is the large-scale memory of that growth. In the visible map, galaxies act as traces of this pattern. They are not the whole content of the structure, but in this section they remain the part that is directly seen. Euclid's census allows astronomers to plot where these traces lie over a vast fraction of the extragalactic sky and over a wide range of cosmic ages. When that plotting is done carefully, broad filaments begin to stand out. These are not thin lines like threads on cloth. They are enormous, elongated regions in which galaxies are more common than average, often stretching across distances that exceed ordinary imagination. They curve, branch, and connect. They're wide enough to contain many systems and long enough to link regions far apart in the survey volume. Between these filaments lie voids. A void is not an absolute emptiness. It is a region where the density of galaxies is much lower than the cosmic average. There may still be isolated galaxies, faint dwarfs, thin gas, and the passage of radiation across it. Yet compared with the denser filaments and junctions, a void appears strikingly open. In a large map, voids become important features, because absence is part of the pattern just as much as presence. A web needs openings as well as strands. The visible universe therefore acquires a texture of concentration and release, a rhythm of crowded lines and broad hollows. This texture is not immediately obvious in a flat view alone. If all galaxies were projected onto one surface without regard to distance, many separate layers would overlap and the pattern would blur. That is why Euclid's depth matters so much. By estimating how far away galaxies are, the survey can place them in broad three-dimensional relation. Once this depth is included, structures that seem accidental in 2 dimensions can be recognized as parts of longer connected forms, while apparent neighbors can be seen to belong to different cosmic depths. The web comes into focus when the survey stops treating the sky as a ceiling and begins treating it as a volume. There is a calm regularity to this large-scale arrangement. The web is complex, but it is not chaotic in the everyday sense. Its filaments are not tangled at random. Its open regions are not carved without order. Statistical measures show repeating properties across different survey volumes, and large cosmological simulations based on accepted physics reproduce web-like patterns with remarkable consistency. This does not mean every detail is predicted in advance. The exact placement of a given galaxy or the precise shape of a particular filament depends on the history of local growth. But the general existence of a connected network of denser and emptier regions is a stable expectation of modern cosmology, and observations confirm it. Euclid's contribution is to measure this visible pattern at scale and with uniformity across a huge domain. Earlier surveys already reveal the web, but Euclid extends the map with the combination of wide area, great depth, and image quality needed for its larger goals. In this 5th region of the script, the mission's value lies in showing that the visible universe itself carries the imprint of a deeper arrangement. Even before any hidden component is inferred directly, the galaxies do not behave like independent lights scattered through empty space. They belong to a larger topography. This topography also changes the meaning of distance. A lone galaxy in a dark field can seem detached, solitary. A web map removes that impression. It shows relation. One system belongs to a filament joins a broader junction, and surrounding that junction are lower density expanses that help define its form. The large-scale universe becomes less like a box filled with separate objects and more like a terrain made of probability, growth, and the long action of gravity on an expanding background. The image is useful so long as it remains modest. The web is not a solid scaffold in the ordinary sense. It is a pattern in distribution, a large-scale arrangement of where galaxies are more and less likely to be found. Seen this way, the visible cosmos no longer appears complete merely because it is bright in places. Its very pattern suggests that brightness has been arranged by wider processes. The filaments, the branching lanes, and the open voids together tell a story of uneven growth from early irregularity to mature structure. Euclid does not invent this story. It reads it from the placement of galaxies across the sky and through cosmic time. The visible universe, once counted, now reveals itself as connected form. Where the visible web of galaxies meets and thickens, there appear its heaviest knots. These are galaxy clusters, the largest gravitationally bound systems in the present-day universe. In the wide pattern of filaments and voids, they occupy the major intersections, the places where many cosmic streams seem to converge. A cluster is not a single galaxy enlarged. It is a gathering of many galaxies held together within one deep gravitational environment, along with large quantities of hot thin gas spread between them. In this next inward region of the subject, the map no longer rests mainly on long strands and open spaces. It settles into the dense luminous nodes that anchor the web. A cluster can contain from hundreds to thousands of galaxies. Some are large spirals or elliptical systems. Many others are smaller companions, dwarf galaxies, and faint members that are difficult to see individually at great distance. From afar, a rich cluster can resemble a crowded city of galaxies, concentrated into a comparatively compact region when set against the emptiness around it. Yet even this crowded appearance gives only part of the physical picture. The galaxies are the most obvious visible residents, but they do not occupy most of the space inside the cluster. Between them lies intracluster gas, a very hot and very diffuse plasma, meaning matter so heated that electrons are no longer bound to atomic nuclei. Though thin, this gas is spread through such a large volume that it contributes a major share of the ordinary matter present. This intracluster gas is one of the reasons clusters matter so much in cosmology. A cluster gathers many forms of ordinary matter into one measurable system. Starlight marks the galaxies themselves. X-ray observations from other observatories reveal the hot gas between them. The member galaxies move through the cluster under the pull of the common gravitational field. In this way, a cluster becomes a place where several visible traces coexist. It is a natural laboratory of collected matter. Euclid sees clusters as especially important landmarks because they stand out within the large-scale map. If filaments are the roads of the cosmic web, then clusters are its major junctions. Matter tends to flow along the filaments over long periods, and the densest nodes grow where these channels meet. The process unfolds over billions of years as gravity gathers material from the surroundings, and as smaller groups and galaxies fall inward or become bound to the larger whole. The cluster, therefore, carries a long history of accumulation. It is a mature structure built gradually within the wider web. In visible images, many clusters show a dominant central galaxy, often an enormous elliptical system that outshines most of its neighbours. Around it lie other galaxies with differing forms and brightness, arranged not as a neat ring, but as an uneven population distributed through the cluster volume. Some members are old and red, with little ongoing star formation. Others retain more obvious structure or signs of disturbance. In a rich cluster, the variety of galaxies suggests that the environment is both crowded and transformative. Galaxies do not evolve there in isolation. They move through hot gas, experience encounters with neighbours, and respond to the tidal pull of the whole system. Yet the most important feature of clusters for this script is not their beauty or diversity. It is the mismatch between what shines and what gravity requires. When astronomers compare the visible contents of a cluster with the motions of its galaxies and the properties of its hot gas, they find that the luminous part is not enough to account for the full gravitational field. The stars and gas are substantial, but they do not make up the whole mass that appears to be present. This conclusion does not depend on one striking object alone. It emerges again and again across many clusters studied by different methods. In these dense nodes of the web, the visible matter is easier to inventory than in more diffuse regions, and that very clarity makes the incompleteness harder to ignore. For this reason, clusters become anchors for the argument that the visible universe is not the whole physical one. A cluster gathers enough ordinary matter to be impressive. It contains huge galaxies, vast reservoirs of hot gas, and the accumulated history of many mergers and infalls. If any kind of system might seem sufficient in visible mass, it would be one of these. Yet the accounting still comes up short. The ordinary matter is rich, but not rich enough. Euclid contributes to the study of clusters by finding them in great numbers across large areas. A cluster population measured consistently, becomes a way of tracing how the densest nodes of structure appear and grow. The survey can identify concentrations of galaxies, measure their member distributions, and place them within the surrounding web. It can compare nearer clusters, seen in more recent cosmic times, with more distant ones, seen earlier in the history of structure. In this way, the clusters are not isolated curiosities. They are part of a statistical landscape. The importance of that landscape lies in scale. A single cluster can teach much about environment and mass, but many clusters together reveal how the most concentrated visible structures populate the cosmos. They show where the web thickens, where matter has gathered most strongly, and how common or rare such dense environments are at different epochs. This is one reason they stand out in Euclid's mission. They are bright enough and rich enough to be identified across great distances, yet large enough to speak directly to cosmological growth. In this sixth region of the story, the phrase "part of the universe is missing" begins to sound less like a dramatic claim and more like a sober result of comparison. Here is a place where ordinary matter is abundant, organized, and measurable. Here are stars within many separate galaxies. Here is gas spread across the cluster in enormous quantities. Here is a system large enough to anchor a section of the cosmic web. And still, when the total is weighed against the gravitational behavior of the cluster, the visible share remains only part of the account. So the journey inward pauses at these great nodes. The cluster is a gathering place of galaxies, gas, history, and gravitational influence. It marks one of the most substantial visible expressions of cosmic structure, but it also marks a limit of appearances. Even where matter is gathered most dramatically into view, the light does not tell the whole story. The densest luminous knots in the web still point beyond themselves. After the great visible nodes of the cosmic web come the paths that light takes around them. This is a deeper layer of the same reality. A galaxy cluster or a massive galaxy does not merely sit in space as a luminous object to be counted. Its mass changes the space around it in a way that affects passing light. In ordinary experience, light seems to travel in straight lines unless it meets a surface, a lens, or a cloud. In the cosmos, gravity itself can play the part of a lens. It can bend, redirect, stretch, and magnify the light from more distant sources. This effect is called gravitational lensing, and it becomes one of the clearest ways to learn that the visible universe is not the whole material one. The idea is simple in outline even if the underlying physics is profound. Mass influences the geometry of space-time, meaning the structure within which matter and light move. When light from a distant galaxy passes near a concentration of mass on its way to the observer, its path is curved. The light still travels locally at the speed of light, but the route it follows through curved space-time is no longer the route it would take in the absence of that mass. The result is that the distant object can appear shifted in position, distorted in shape, brightened, multiplied into several images, or stretched into arcs and rings. None of this requires the lensing mass to shine. Gravity acts whether the matter is luminous or dark. This is why lensing matters so deeply in the present story. Starlight and glowing gas reveal ordinary matter because they emit radiation that telescopes can record directly. Dark matter, if it does not emit or absorb light in a familiar way, cannot be photographed in the same sense. Yet if dark matter contributes to the total gravitational field, then it also contributes to the bending of light. Gravitational lensing therefore becomes a way of tracing mass itself rather than brightness alone. It allows astronomers to compare the map of what shines with the map of what bends passing light. Where the two fail to match fully, the difference carries meaning. The clearest cases are sometimes called strong gravitational lenses. These occur when the alignment between a foreground mass and a more distant source is especially favourable. If a distant galaxy lies closely behind a massive foreground galaxy or cluster along the line of sight, the background light can be bent so strongly that it forms long arcs around the foreground object. In very symmetric cases, the light can appear as a nearly complete ring, known as an Einstein ring. In other cases, the source appears in several separated images, each one a different path by which its light reaches the observer. These are among the most striking visual signs that gravity reshapes the appearance of the sky. Such images are beautiful, but their scientific value is more than visual. The size and arrangement of the arcs or images depend on how mass is distributed in the foreground lens. A foreground galaxy may shine strongly at its centre, yet the lensing pattern often shows that the bending influence extends well beyond the bright visible region. A cluster may contain many luminous members, but the arcs behind it reveal a broader gravitational field than the luminous galaxies alone would suggest. In this way, lensing turns the background sky into a measuring screen. The distorted source acts like a test signal passing through an otherwise invisible field of mass. Euclid is especially well suited to finding these effects because it combines wide sky coverage with sharp imaging. Over large areas, it can detect many cases in which foreground galaxies or clusters distort the appearance of more distant galaxies behind them. Already in its early data, Euclid reveals hundreds of strong lens candidates, and the mission is expected to find many thousands more as the survey continues. This matters because strong lenses are rare in any single small field. Their value grows when they are collected in large, uniform numbers. Then they cease to be isolated curiosities and become part of a systematic map of how mass is arranged across the sky. There is something quietly decisive about gravitational lensing. The effect does not ask whether matter is visible. It responds only to the total gravitational influence along the line of sight. A foreground structure may contain stars, dust, gas, stellar remnants, and an additional unseen component. The light from a more distant source is bent by the total. This makes lensing different from methods that rely on emitted light or on assumptions about how luminous matter traces mass. Lensing is not completely free of interpretation, because the geometry of source, lens, and observer must still be understood, yet it is direct in a special sense. It measures the action of gravity on light itself. That directness is one reason the effect carries so much weight in modern cosmology. When multiple independent methods all suggest that visible matter is not enough to explain observed gravity, the case becomes stronger. Gravitational lensing is one of those methods, and it is powerful because it depends on neither the internal motions of stars within a galaxy, nor only on the temperature of gas in a cluster. Instead, it reads the curvature imprinted on a beam of light that crosses the foreground structure. The background galaxy need not know anything about the lens. Its light is altered simply by passing through the field. In this region of the subject, the phrase "part of the universe is missing" becomes more exact. What is missing is not a piece torn away from the cosmos, nor a gap where reality fails. What is missing is a sufficient amount of visible matter to account for the bending observed. The light from distant galaxies arrives bearing distortions that correspond to mass. When astronomers compare those distortions with the luminous foreground objects alone, the luminous part often falls short. The lens is stronger than the visible matter by itself would predict. The missing part is therefore not a missing place, but a missing share in the visible inventory. Euclid studies this bent light across great stretches of sky and cosmic history, turning a phenomenon once seen in individual dramatic examples into part of a wider cosmological method. The path of light becomes evidence. The background sky becomes a field of probes. The foreground universe becomes readable not only by what it emits, but by what it does to passing radiation. In that calm and exact way, gravitational lensing opens a deeper view than light alone can provide. The visible cosmos remains present, but its apparent boundaries loosen. Light does not merely show what is there, it also records what it has passed through. Not all gravitational lensing announces itself with rings, arcs, or obvious multiple images. Most of the time, the effect is much quieter. A distant galaxy does not become a dramatic curve around a massive foreground object. Instead, its apparent shape is altered only slightly. It may seem a little more stretched in one direction, a little more aligned with neighbouring distortions, or a little displaced from the appearance it would have in the absence of intervening mass. This gentler regime is called weak gravitational lensing. It is weak not because gravity itself is unimportant, but because the visible effect on any one background galaxy is small. This smallness changes the entire character of the measurement. In strong lensing, a single remarkable image can already reveal that mass has bent the light. In weak lensing, one galaxy alone is usually not enough. Galaxies are born with many natural shapes. Some are rounder, some flatter, some smooth, some irregular. From a single image, no observer can say with certainty whether a faint elongation comes from lensing or from the galaxy's own original form. The signal hides inside ordinary variety. It can be recovered only statistically, by studying very large populations and looking for patterns that no random collection of intrinsic shapes would produce on its own. This is the core of Euclid's main lensing task. The mission is not built mainly to collect a few extraordinary gravitational spectacles. Its central aim is to measure the tiny distortions of enormous numbers of background galaxies across a vast part of the sky. When enough galaxies are examined together, the small lensing effects begin to add up. Individual uncertainty remains, but collective behavior becomes meaningful. A slight tendency for neighboring galaxies to appear stretched in related ways can reveal the influence of the foreground matter through which their light has passed. Astronomers often call this large-scale pattern cosmic shear, using the word shear to mean a coherent stretching or skewing of shapes. The idea is delicate but powerful. If the universe between observer and source were perfectly smooth, then distant galaxies would still show their own natural variety of forms, but those forms would not display the same kind of broad, correlated imprint from line-of-sight structure. Weak lensing adds just such an imprint. The effect is usually tiny, much smaller than the original differences among galaxies themselves, yet it is not random. It reflects the cumulative gravitational influence of matter distributed along the path of the light. One faint galaxy may carry too little information alone, but millions and eventually billions together begin to reveal a shared distortion field. This is why image quality matters so deeply for Euclid. To study weak lensing, the telescope must record galaxy shapes with exceptional stability. Any instrument blurs light to some degree. Mirrors, detectors, thermal conditions, pointing accuracy, and optical imperfections all affect the final image. For many kinds of astronomy, such blur is merely a technical nuisance that can be tolerated within reason. For weak lensing, it becomes central. the distortions caused by the telescope itself can be of the same general kind as the distortions caused by gravity, and often much larger. If the instrument slightly stretches all sources in one direction because of its own optics, that false signal could mimic the cosmic one unless it is precisely understood and removed. Weak lensing therefore depends not only on seeing galaxies, but on knowing exactly how the telescope sees them. The difficulty does not end there. The galaxies used for weak lensing are often distant and faint. Their light has been travelling for billions of years, and their apparent sizes on the detector are small. Some are only modestly resolved. Noise from the measurement process, overlapping sources, and changes in observational conditions all complicate the effort to recover their true apparent shapes, so the science proceeds with patience. Shapes are measured, the response of the instrument is modelled, statistical biases are tested, and large samples are built until the weak signal can rise above the scatter of individual variation. Because of this, weak lensing is never a science of haste. It asks for breadth, consistency, and very large numbers. Euclid is designed for exactly this kind of work. It surveys a huge area of extragalactic sky and measures the shapes of vast populations of galaxies over a long span of cosmic history. The farther the background sources lie, the more intervening structure their light has crossed on average, and the more lensing information they can contain. This does not mean the effect grows in a simple, steady way for every individual case, but it does mean that a deep survey of remote galaxies becomes especially valuable for revealing the accumulated action of foreground matter. The statistical nature of weak lensing also changes the way the sky is interpreted. In ordinary imaging, a galaxy is often treated as an object with its own local story. In weak lensing, the same galaxy becomes partly a messenger from the space between. Its observed shape contains information not only about itself, but about the mass distribution along the line of sight. The source and the path are joined in the observation. A galaxy is never read as pure autobiography. It is read as biography plus journey. When many such journeys are compared, a quiet coherence emerges. Galaxies that lie near one another on the sky, and especially those sitting behind similar foreground structure, can show related distortions. No single alignment proves very much, because chance can imitate structure on small samples. But across huge surveys, chance and coherent distortion behave differently. Random intrinsic shapes tend to average away. The lensing imprint, because it is shared statistically by many background sources, remains. In this manner, weak lensing converts immense numbers into clarity. This clarity is subtle rather than dramatic. A person looking casually at a Euclid image will not see the dark universe outlined like ink on paper. The effect is too small for that. What appears instead is a sky full of galaxies whose shapes, taken one by one, seem ordinary enough. The hidden information lies in their collective tendencies. Weak lensing belongs to that class of science in which truth emerges not from spectacle, but from accumulation. It is the patience of the survey that gives the phenomenon its force. So in this eighth region of the script, the missing part of the universe leaves a statistical trace. It does not shine, and in most cases it does not produce a dramatic lens, yet it still acts on light. It leaves behind a faint, widespread pattern of stretching that can be measured only when the sky is studied at enormous scale and with unusual discipline. Euclid works in that quiet regime, where tiny distortions spread across millions of galaxies become evidence that the visible cosmos is shaped by more mass than light alone reveals. A field of weak distortions becomes most meaningful when it's no longer treated as a collection of separate stretched galaxies. but as a map of the matter that causes the stretching. This is the next inward layer of the subject. The previous region remains with the tiny lensing signal spread across immense samples of background galaxies. Now the attention shifts to what can be built from that signal. The scattered traces of gravitational influence are gathered together and translated into a picture of mass distribution. It is not a picture in the ordinary visual sense, because the mass being traced does not have to shine. Yet it is still a map, with denser regions, thinner regions, broad structures, and changing depth. The first step in such a map is to recognize that weak lensing measures not isolated objects but a field. Each background galaxy carries a small amount of information about the cumulative mass lying between source and observer. When millions of such galaxies are measured across a wide area, their distortions can be combined statistically to infer where the foreground gravitational influence is stronger or weaker. A region in which many background galaxies show a related pattern of shear suggests a greater concentration of intervening mass. A region where the pattern is weaker suggests less. In this way, the survey begins to recover a continuous gravitational landscape from many individual lines of sight. This landscape is not perfectly direct. Weak lensing does not place a label on each clump of matter and announce its precise contents. This signal is an integrated effect along the path of the light. Every galaxy image contains the accumulated influence of matter, distributed over a broad stretch of space between the source and the telescope. A mass map therefore requires careful inference. Astronomers use the measured distortions to reconstruct a projected distribution of matter on the sky, meaning a map of how mass appears when its effects are gathered along the line of sight. Even this projected view is powerful. It reveals peaks, ridges, extended concentrations, and large connected patterns that do not depend on visible light alone. The result can look familiar in one sense and surprising in another. Some of the denser regions in the reconstructed map line up with visible clusters and filaments already known from galaxy surveys. This is not unexpected, because luminous galaxies do trace part of the underlying structure. Yet the match is not simply one of bright shape copied into hidden form. The mass distribution often extends beyond the most luminous visible areas, and the contrast between visible matter and total gravitating matter becomes clearer. A bright cluster may sit inside a broader concentration. A filament of galaxies may correspond to an even more extensive ridge in the mass map. The reconstructed field therefore preserves the visible universe, but places it inside a wider framework. This is one of the quiet strengths of lensing. It does not ask matter to emit light in order to be counted. A region rich in dark matter can influence background shapes whether or not it contains many bright galaxies. A place with fewer visible objects can still contribute to the lensing field if enough mass lies there. The map that emerges is therefore not a portrait of brightness, but a portrait of gravitational effect. It is a way of drawing the hidden structure without requiring the hidden structure to glow. Euclid is designed to make this kind of mapping an exceptional scale. Because it measures galaxy shapes across a very large area and across a long span of cosmic time, it can reconstruct matter not only in isolated patches, but across wide connected survey regions. This matters because hidden structure, like visible structure, is not best understood in fragments alone. A small map may show a single mass concentration. A wide map begins to reveal how many concentrations join into larger patterns, how filaments connect denser nodes, and how lower density regions open between them. The hidden matter field begins to resemble the large-scale architecture already hinted at by galaxies. but it appears with its own greater continuity. There is also depth in this mapping. The lensing signal depends on the relative distances among observer, lensing matter, and background source. If astronomers sort source galaxies into broad distance layers, they can compare how the inferred mass pattern changes with cosmic epoch. This approach is sometimes called tomography, a word borrowed from other forms of imaging in which slices through a volume are reconstructed from many measurements. In cosmology, the slices are not literal cuts through matter, but layered estimates of structure at different depths in space and time. Euclid uses this principle by combining weak lensing measurements with distance information for its source galaxies. The hidden mass map thus gains thickness. It is no longer only a projected screen. It becomes a sequence of approximate layers. This layered mapping is especially important for understanding cosmic growth. A nearby layer shows the matter field in a more recent state. A more distant layer shows it earlier, when structure is less mature. By comparing these layers, astronomers can trace how the hidden scaffolding of the universe develops over billions of years. The map ceases to be static, it becomes historical. Matter concentration, filament growth, and the relative prominence of dense nodes can all be studied as features that evolve. Even so, uncertainty remains part of the discipline. Weak lensing maps are statistical reconstructions, not direct snapshots with sharp physical edges around every structure. Noise in the galaxy shapes, uncertainty in distance estimates, limitations of survey coverage, and the smoothing needed to recover the underlying field all affect the final result. Astronomers therefore treat these maps with care. They compare them with simulations, cross-check them with galaxy clustering and cluster catalogues, and quantify the significance of the structures they identify. None of this weakens the method. It simply reflects its nature. The hidden mass field must be inferred with patience because it does not present itself as luminous scenery. In this ninth region of the script, the phrase missing part of the universe gains a more definite visual meaning. The missing part is not missing from gravitational influence. It is present in the distortions of background light and in the reconstructed patterns that follow from these distortions. Euclid helps turn that influence into geography. It shows where matter gathers most strongly, where it stretches into connecting forms, and where it thins into lower density regions, even when much of that matter remains unseen in ordinary light. The visible cosmos becomes one layer in a broader mapped reality. So the path inward reaches a threshold of revelation. What begins as faint, nearly invisible sheer across millions of galaxies becomes a chart of the hidden mass distribution of the universe. This chart does not replace the visible sky, it explains it more fully. Bright galaxies and clusters remain where they are, but they are now set within a larger gravitational terrain that can be traced even where light alone would leave the account incomplete. The invisible is not made luminous, it is made legible. At this stage, the hidden map of mass has already come into view, and with it a powerful reason to believe that the visible universe is not the whole account. But there is an important distinction still to be made within that hiddenness. Not everything that is hard to see belongs to the same mystery. This next inward region concerns ordinary matter that goes missing from view, not because it is dark matter, but because it is thin, hot, spread out, and difficult to detect. Astronomers call ordinary matter baryonic matter, or baryons for short, meaning the matter made of atoms and of the familiar particles that build stars, planets, gas clouds, rocks, oceans, and living bodies. The long search for missing ordinary matter is therefore not the search for dark matter. It is the search for matter of the ordinary kind that simply fails to show itself easily. The difference matters because the two problems begin from different clues. Dark matter is inferred because the observed gravity of galaxies, clusters, and large-scale structure exceeds what visible ordinary matter appears able to provide. Missing ordinary matter is inferred in another way. Observations of the early universe, especially the cosmic microwave background, reveal how much ordinary matter should exist in total. This ancient radiation acts like a preserved record of the young cosmos, and allows cosmologists to estimate the overall abundance of baryons with great precision. That earlier counting is clear. The trouble appears later, when astronomers try to find the same matter in the more recent universe. If they count the stars inside galaxies, the cold gas within galaxies, and the dust mixed through galactic space, they do not recover the full expected amount. Adding the hotter gas in galaxy clusters helps, and so does adding gas in the broad halos around galaxies. But for many years a large fraction of ordinary matter still seems absent from the inventory. This absence produces what is known as the missing baryon problem. The word missing here does not mean that atoms have vanished from existence. It means they are missing from direct observational accounting. The theory of the early universe says they should still be present somewhere, but the usual places where astronomers look do not contain enough. This missing ordinary matter is not thought to hide in compact secret worlds or dark solid bodies drifting through space. The evidence points instead toward a very diffuse state. Much of it appears to lie around galaxies in extended halos and, beyond those halos, in the intergalactic medium, the thin gas that stretches through the cosmic web between galaxies. Some of this matter is warm, some hot, and some so tenuous that it emits very little detectable radiation. This makes it difficult to see directly. A galaxy filled with stars shines strongly because matter there is dense and luminous. Gas spread over enormous volumes behaves differently. Even when the total mass is large, the radiation from each part can be faint. This is why ordinary matter can be both present and elusive. In a galaxy, gas can cool, condense, and form stars. In the broader spaces around and between galaxies, much of it remains diffuse. It may be heated by shocks as structure forms, by the growth of clusters, by energetic activity from galaxies, or by the long stirring of the cosmic web itself. When gas becomes very thin and very hot, it can fall into an awkward observational range. It may be too sparse to glow strongly, too ionized for some familiar signatures, and too extended to stand out against background noise. The missing matter problem, therefore, becomes a problem of phase and location. The baryons are not absent from the universe. They are absent from the easiest forms of detection. The regions most relevant here are the circumgalactic medium and the intergalactic medium. The circumgalactic medium is the broad reservoir of gas surrounding a galaxy, beyond its bright stellar body. It is not empty space around the galaxy, but a real environment through which matter can flow inward and outward. The intergalactic medium lies farther out, occupying the enormous spaces between galaxies and along the filaments of the cosmic web. When astronomers speak of the warm-hot intergalactic medium, they mean a phase of gas heated enough to become difficult to trace, yet still ordinary in composition. This component has long been expected from simulations of structure formation. Over the past years, evidence for this diffuse baryonic reservoir grows stronger. X-ray observations reveal hot gas in cluster environments and in some filaments linking clusters. Ultraviolet absorption studies detect certain ionized elements in front of bright background sources, showing that thin gas lies where little visible matter is otherwise apparent, More recently, fast radio bursts add a powerful new tool. These brief radio flashes cross enormous cosmic distances, and on their way to Earth they are delayed by free electrons spread through the intervening gas. By measuring that delay, astronomers estimate how much ordinary ionized matter lies along the path. With enough well-localized bursts, they can show that much of the long-missing baryonic matter resides in the thin fog between galaxies. With another substantial share in galaxy halos, this finding changes the meaning of absence. The missing ordinary matter is not some exotic new substance. It is mostly familiar atomic material in unfamiliar conditions. Protons and electrons remain where cosmology says they should broadly be, but they are distributed in ways that make them hard to see. Instead of gathering mainly inside bright galaxies, much of the baryonic content of the late universe appears to drift through extended reservoirs around galaxies and through the filamentary spaces between them. The visible parts of galaxies are therefore only a partial expression of ordinary matter, just as they are only a partial expression of total matter more broadly. It is important not to confuse this with dark matter. Dark matter is still required because even after the missing baryons are better accounted for, ordinary matter does not provide enough gravity to explain lensing maps, galaxy rotation, cluster dynamics, and the large-scale growth of structure. Recovering the missing ordinary baryons does not remove the dark matter problem. It solves a different gap in the cosmic inventory. One gap concerns the whereabouts of normal atomic matter. The other concerns the existence of additional gravitating matter that does not behave like ordinary atoms at all. In this 10th region of the script, the title takes on a more careful form. Part of the universe seems missing for two different reasons. One part is hidden because it is dark matter, detected through gravity but not through ordinary light. Another part is hidden because it is ordinary matter spread so thinly around and between galaxies that it escapes simple detection. The first points toward an unknown component of nature. The second points toward a hidden state of familiar matter. Both deepen the sense that the bright contents of the sky are only a fraction of what is really there, so the path inward pauses in a medium that is easy to overlook because it is almost the opposite of the stars. It is not compact, not bright, not sharply bounded. It is thin gas in broad halos and long intergalactic strands. Ordinary matter dissolved into the vastness between the luminous islands of the cosmos. Once again, the universe proves fuller than it first appears. Once the hidden and visible contents of the cosmos have been distinguished, the next inward layer concerns how those contents change their arrangement over time. Structure does not appear all at once in its mature form. The universe on the larger scales is not born as a finished web of filaments, clusters, and voids. It grows toward that condition. This growth is one of the central themes of modern cosmology, and Euclid is built to observe it across a very long span of cosmic history. The mission does not watch individual galaxies drift in real time, because the relevant changes are far too slow for a human lifetime. Instead, it compares different cosmic ages by looking to different depths. Nearer regions show a later stage of development. More distant regions show an earlier one. In this way, the survey turns distance into a sequence of growth. The starting point for this growth lies in the early universe, when matter is distributed much more smoothly than it appears today. Smooth does not mean perfectly uniform. Tiny variations already exist, with some regions containing slightly more matter than others. These differences are very small at first, but they matter because gravity responds to them. A place with a little more matter exerts a little more pull. Over long spans, That slight advantage allows it to gather still more material from its surroundings. The difference then grows. Regions that begin denser become the seeds of later structure. Regions that begin thinner lose ground by comparison. This gradual amplification is the basis of cosmic growth. Dark matter plays a major role in this process because it does not need to shine in order to exert gravity. It begins forming broad gravitational wells early in cosmic history, and ordinary matter responds to those wells. Gas falls inward, though not in exactly the same way at every time and place. Pressure, heating, cooling, and radiation all affect the behavior of ordinary matter, while dark matter mainly participates through gravity. Over time, this shared but unequal development leads to the large-scale structure seen in later epochs. The dark component helps shape the underlying pattern, while ordinary matter eventually forms galaxies, stars, and the visible features that telescopes record directly. This long development is not uniform across all scales. Small structures can begin forming before larger ones are fully assembled, while larger environments continue to grow by drawing in smaller ones. Groups of galaxies merge into clusters. Filaments thicken as matter continues to stream along them. Voids expand in a relative sense because matter drains away toward denser regions. The cosmic web therefore matures through a combination of accumulation and contrast. Dense regions become denser. Sparse regions become more clearly sparse. The overall pattern remains web-like, but its strength and definition increase with time. Euclid studies this maturation by surveying galaxies and matter over roughly the last 10 billion years. That interval covers a large fraction of the period during which structure grows from earlier, less developed forms into the more strongly clustered universe seen nearby. Because the light from distant galaxies began its journey long ago, Euclid can compare many stages of that process within one coordinated map. A nearer sample contains galaxies whose light leaves them more recently, so it reflects a later cosmic state. A farther sample contains galaxies seen at an earlier stage. By arranging these samples in order of distance, astronomers trace how clustering changes across time. The change appears in several related ways. One is the increasing tendency of galaxies to gather into stronger patterns rather than remain more evenly spread. In earlier epochs, the web is present in a less mature form. Dense knots are less fully built, and the contrast between filaments and voids is weaker than it becomes later. In more recent epochs, clusters are richer, filaments are more pronounced, and the large-scale pattern stands out more clearly. Another way is through the hidden mass map inferred from weak lensing. There, too, the matter field can be compared across depth, showing how the gravitational scaffolding becomes more developed with time. This is why Euclid combines galaxy clustering and weak lensing. The first shows where visible traces of structure are found. The second reveals how total matter, including dark matter, is distributed. When both are measured across different cosmic ages, they allow astronomers to ask how fast structure grows and whether that growth follows the expectations of the standard cosmological picture. The answer matters because growth depends on the balance of ingredients in the universe. If gravity gathers matter one way, and cosmic expansion affects the background another way, then the resulting rate of structure formation becomes a sensitive test of the overall model. There is a calm precision in this test. Astronomers do not simply ask whether galaxies exist earlier or later. They ask how strongly matter is clumped at different times and on different scales. They measure correlation, which in this context means the tendency of galaxies or lensing signals to be related across distance rather than scattered independently. They measure the abundance of clusters, the shape of the web, and the statistical strength of shear across layers of depth. All of these quantities are indirect expressions of one broad reality. The universe does not remain equally mixed. It develops pattern. Observations from many earlier surveys already support this picture of growth, and Euclid extends that work with wider area, deeper reach, and the ability to connect visible structure with hidden mass over a large fraction of the sky. Its value lies not in replacing the existing framework with sudden novelty, but in measuring that framework more finely and more broadly. This is important because small deviations can matter. A universe in which structure grows a little faster or a little slower than expected may point to changes in the behavior of dark energy, the properties of dark matter, or even the way gravity operates on the largest scales. At present, observations indicate broad agreement with the standard picture. Though some tensions and open questions remain under study, Euclid helps address those uncertainties by enlarging the data set and improving the map. In this 11th region of the script, the phrase "part of the universe is missing" becomes temporal as well as material. The hidden part is not only what fails to shine, it is also the long process by which today's visible and invisible structure comes into being. A nearby cluster is not merely a present object. It is the late outcome of billions of years of accumulation. A distant filament is not merely far away. It is a younger version of a structure still in development. Euclid makes this growth legible by observing many ages at once, so the inward path reaches a universe that is no longer static scenery. It is a changing distribution of matter, with tiny early differences gradually enlarged into the vast architecture now spread across the sky. Dense regions strengthen, open regions empty further, and the web matures through time. The visible cosmos and the hidden mass field both carry the marks of that slow development. What seems at first like a fixed celestial arrangement becomes, under Euclid's view, a record of ongoing formation. As the growth of structure becomes measurable across time, another layer of the cosmos begins to reveal itself through the same broad survey. The matter of the universe does not only gather into filaments, clusters, and voids. The space through which all of that structure is spread also changes in scale. This next inward region concerns that large geometry. It concerns distance itself, and how astronomers learn the history of cosmic expansion by studying the arrangement of galaxies across enormous volumes. Euclid approaches this problem not by watching space stretch directly, but by reading subtle regularities preserved within the distribution of matter. The universe expands, which means that on the largest scales the average separation between distant galaxies increases with time. This does not mean that every bound system grows larger. Galaxies, solar systems, stars, and planets are held together by forces that dominate on their own scales. The expansion matters most across the vast reaches between large structures. It is a property of the cosmos as a whole, visible in the recession of distant galaxies and in the changing scale of the observable universe over cosmic time. Once this is understood, a new challenge appears. It is not enough to know that expansion happens. Cosmology seeks to know how fast it proceeds at different ages, and whether that rate changes in a smooth or more complicated way. To answer that, astronomers need distance markers that can be recognized across large parts of the sky. Some methods rely on particular kinds of stars or exploding stars as standard candles, meaning objects with known brightness that help estimate distance by how bright they appear. Euclid contributes in another broad way. It uses the large-scale clustering of galaxies themselves, which contains a faint but measurable preferred scale inherited from the early universe. This scale survives as a subtle statistical feature in the cosmic web. It is known as baryon acoustic oscillations. The phrase sounds technical, but its physical meaning is straightforward when stated gently. In the very early universe, before atoms fully form, ordinary matter and radiation are tightly coupled in a hot, dense plasma. Pressure waves move through this plasma, rather as sound waves move through air, though under far more extreme conditions. As the young universe cools and atoms eventually form, radiation decouples and travels freely, while ordinary matter is left with a slight imprint of those earlier waves. The imprint does not survive as visible ripples in the everyday sense. Instead, it leaves a weak preference in the later distribution of galaxies, a tendency for pairs of galaxies to be found at a certain characteristic separation more often than pure chance would suggest. This preferred scale becomes a cosmic ruler. It is not a ruler held in the hand, nor a line drawn across space, but a known physical length imprinted early and later, measurable statistically in galaxy clustering. If astronomers observe how large this scale appears across the sky and along the line of sight at different distances, they can infer how the geometry of the universe has expanded over time. A ruler of fixed physical size appears differently depending on the structure of the space through which it is observed. In that calm way, the early plasma leaves behind a later tool for measuring cosmic distance. Euclid is built to use this ruler over a large fraction of the sky and across a wide span of history. Its survey records the positions of galaxies in immense numbers, and with distance information it can recover how clustering behaves in 3 dimensions. The baryon acoustic oscillation signal is not obvious to the eye in any one map. It is a statistical excess at a certain scale, delicate and broad, revealed only when huge galaxy samples are analysed together. This makes Euclid especially suitable for the task. A wide survey reduces the risk that local peculiarities dominate the result. A deep survey allows the ruler to be measured at several different epochs. The geometry of expansion can then be traced rather than guessed. There is a useful difference here between visible structure and geometric measurement. The cosmic web shows how matter grows unevenly under gravity. The baryon acoustic oscillation scale shows how the whole expanding framework carries that structure outward over time. One concerns clustering strength and pattern. The other concerns the large metric background in which that pattern is embedded. The two are related because both live in the same universe, and both are measured from the same survey, but they are not identical. In this 12th region of the script, the emphasis remains on the ruler and the geometry it reveals. Redshift is central once again. Because the light from more distant galaxies is more strongly stretched, it provides a way to place those galaxies at different broad depths in time. When Euclid measures how the preferred clustering scale appears at different redshifts, it is effectively examining the size of the cosmic ruler in different eras. If the expansion history were different, the apparent dimensions of that ruler would differ in measurable ways. By comparing the observed scale with the expected physical one, astronomers can infer the expansion rate and the way cosmic distances have accumulated across time. This work is statistical, but it is not vague. Large numbers give it strength. Euclid does not depend on a few rare special objects for this purpose. It depends on the collective arrangement of galaxies over vast survey volumes. Every accurately placed galaxy becomes part of a larger measurement of cosmic geometry. Even the emptier regions matter, because the ruler is defined not by individual systems, but by the full pattern of separations across the galaxy population. The survey thus turns the cosmic web into an instrument for distance measurement. What emerges is a picture of expansion, that can be compared with the standard cosmological model. Observations from many methods already show that the expansion history is not the simple slowing that would occur in a universe governed only by ordinary and dark matter. Instead, the late-time expansion reflects the influence of dark energy, or something that behaves like it. Euclid helps constrain this history by measuring both galaxy clustering and weak lensing together. In this section, however, the lensing map stays in the background. The main point is that clustering contains geometry as well as structure. The arrangement of galaxies is not only a record of where matter grows, it is also a record of how space itself has stretched. So the path inward reaches a more abstract but no less physical layer of the cosmos. Beneath the visible galaxies, beneath the hidden matter field that shapes them, there is the expanding geometry that carries all large structures apart on average through time. Euclid reads that geometry through a ruler laid down in the early universe and preserved as a faint preference in galaxy separations. This sky becomes not just a map of objects, and not just a map of mass, but a map of distance history. Space itself enters the account. When the large geometry of the universe is measured across time, one result stands apart for its quiet strangeness. The expansion of the cosmos does not simply continue under gravity in the way earlier intuition might suggest. Matter attracts matter on large scales. This attraction should work against expansion by slowing it over time. Yet observations of the late universe show something different. The expansion is not merely continuing, it is accelerating. Distant galaxies are, on average, being carried apart in such a way that the rate of expansion changes over time in a manner that cannot be explained by ordinary matter and dark matter alone. This is the next inward region of the subject, where the problem is no longer only hidden mass or large-scale geometry, but the deeper agent behind the changing pace of the cosmic expansion itself. The discovery of accelerated expansion changes the meaning of cosmic history. In a universe filled only with matter and radiation, expansion after the Big Bang would still proceed, but gravity would steadily resist it. The pace would slow, even if it never fully stopped. Instead, the observed late-time behavior indicates that some additional influence dominates on the larger scales. It does not pull structures together in the familiar way matter does. It affects the background evolution of the universe in the opposite sense, allowing distances between far-separated galaxies to grow faster over time. This is why the problem becomes so central. It concerns not a local anomaly, not one class of objects, but the overall fate and behavior of the cosmos. The name most often given to this influence is dark energy. The phrase does not describe a known substance in the way water or gas does. It is a label for the unknown cause of the observed acceleration. In the simplest cosmological model, dark energy behaves like a constant energy density of empty space itself. This idea is often called the cosmological constant. In that picture, even when matter thins out as the universe expands, this constant background term remains, and eventually it dominates the large-scale dynamics. The result is accelerated expansion. The model is mathematically simple and has described many observations remarkably well, which is why it remains the standard reference point. But the simplicity of the term does not make the underlying reality fully understood. It gives the behavior a name and a place in the equations. Yet the physical origin remains uncertain. This uncertainty is one reason Euclid matters so much. The mission is not expected to photograph dark energy directly. Dark energy does not form visible clumps, glowing clouds, or recognizable objects that a telescope can isolate in an image. Instead, its presence is inferred from the way cosmic expansion unfolds and from the way structure grows under that expansion. Euclid studies both of these effects by measuring galaxy clustering, weak lensing, and the large-scale arrangement of matter across a long stretch of cosmic time. In this section, however, the focus remains on the acceleration itself and the broad interpretive space around it. One possibility is that dark energy truly is something like a constant property of space. In that case, the acceleration reflects the simplest extension of the standard cosmological model, and the large-scale expansion history can be described with relatively few ingredients. Another possibility is that the driving influence changes with time. Instead of a constant background, the effective dark energy could evolve, becoming stronger or weaker across cosmic history. There are many theoretical forms such a change could take, though no single alternative has yet displaced the simpler standard picture. Observations indicate that the simplest model still performs very well, but it remains important to measure the expansion history as precisely as possible, because even small departures could matter. There is also a deeper possibility. The acceleration might not arise from a new energy component at all, but from an incomplete understanding of gravity on the larger scales. General relativity has passed many tests with extraordinary success, from the solar system to compact astrophysical systems. Yet the cosmic acceleration invites astronomers and physicists to ask whether gravity behaves exactly as expected across the full breadth of the universe. If the law of gravity changes subtly over vast distances, then the observed expansion and the growth of structure could differ from the simplest standard predictions. This does not mean that general relativity is casually abandoned. It means that the largest possible scales provide one of the few environments where its limits, if any exist, might become visible. The distinction between dark energy and modified gravity is not easy to make from expansion history alone. Different underlying causes can produce similar broad distance measurements. This is why cosmology values multiple kinds of observation. The expansion of space is one part of the evidence. The rate at which matter clumps into galaxies, filaments, and clusters is another. A theory that reproduces one but fails on the other becomes less convincing. Still, in the present inward step, the essential point is that the acceleration itself is real in the observations, and that it signals a major incompleteness in the current physical account of the universe. This incompleteness has a different tone from the missing ordinary matter problem. Missing baryons are ordinary matter in hard-to-see places and states. Dark matter is gravitating matter that does not shine in familiar ways. Dark energy, or the cause of acceleration, is different again. It concerns the background evolution of the cosmos, rather than simply the inventory of matter within it. The three absences, therefore, belong to different levels of the same cosmic bookkeeping. One is a hidden share of ordinary atoms. One is a hidden mass component. One is a hidden driver of expansion. Together they show how little of the total cosmic content is expressed in the directly visible world of stars and galaxies. Euclid enters this problem by extending the observed reach of precision cosmology. It measures the large-scale distribution of galaxies and matter across billions of years, building a record against which the late-time acceleration can be constrained. The more accurately the geometry and growth of the universe are mapped, the narrower the range of acceptable explanations becomes. In this way, the mission does not promise a dramatic revelation in a single image. It promises something slower and more exact. It tightens the description of how the universe has expanded and how structure has responded to that expansion. In this 13th region of the script, the title approaches its deepest meaning so far. Part of the universe seems missing not only because mass hides from view, but because the visible cosmos gives no direct sensory clue to the force or condition that now dominates its expansion. The stars shine, galaxies cluster, and the web grows. Yet beneath these visible processes, the larger-scale evolution of the cosmos is governed by something still not fully understood. The mystery no longer concerns only what fills the universe. It concerns what drives its changing future. By the time the survey reaches this depth of interpretation, the visible sky, the hidden mass map, the growth of structure, and the expansion history all begin to converge into a single demanding task. The task is not merely to describe the universe, but to test the model used to explain it. This is the next inward region of the subject. Here the question is no longer where galaxies lie, how light bends, or how matter grows when taken one piece at a time. The question becomes whether one coherent cosmological framework can account for all of these measurements together. Euclid is built for this combined test. The standard cosmological model gives a compact description of the large-scale universe. In its simplest widely used form, it assumes that the cosmos contains ordinary matter, dark matter, radiation, and a dark energy component consistent with a cosmological constant, all evolving under general relativity. From this starting point, the model predicts how matter should cluster, how the cosmic web should develop, how light should be lensed, how galaxy separations should preserve the early acoustic ruler, and how the expansion rate should change over time. The power of the model lies in its breadth. It does not explain only one class of observations. It attempts to explain many at once. That breadth is also its vulnerability. A model that makes many linked predictions can fail in many linked ways. If the expansion history appears right but the growth of structure proceeds too quickly or too slowly, there is a problem. If lensing indicates a different amount of clumping than galaxy clustering suggests, there is a problem. If the distance ruler implies one geometry, while the shear field implies another, there is a problem. Euclid addresses this vulnerability by measuring several major observables within one coordinated survey. The same mission that records galaxy positions also measures shapes, estimates distances, identifies clusters, and reconstructs the matter field. This helps reduce the risk that different datasets are being compared across radically different instruments and methods alone. The comparisons can be made within a more unified framework. Two of the most important observables are weak lensing and galaxy clustering. Weak lensing traces the total matter distribution through the small distortions imposed on background galaxy shapes. Galaxy clustering traces the positions of luminous tracers across the cosmic web. These two are related but not identical. Galaxies do not mark matter in a perfectly one-to-one way. They form in certain environments and with a certain efficiency. So the visible galaxy field is said to be biased with respect to the full matter field. This does not mean it is misleading. It means the relation must be modelled. Weak lensing helps by providing a more direct gravitational view of the total matter distribution, while clustering provides the rich three-dimensional pattern of where galaxies actually appear. When the two are combined, they constrain the model much more tightly than either can alone. This combination is valuable because different cosmological ingredients leave different kinds of signatures. A change in the amount of dark matter alters how strongly structure grows. A change in the properties of dark energy alters both the expansion history and, indirectly, the rate of structure formation. a modification of gravity can shift how matter responds to the background expansion and how lensing traces the resulting field. No single measurement by itself cleanly separates all these possibilities, but several measurements together can begin to do so. Euclid's role is to bring these lines of evidence into common contact. Even with that strength, the testing is delicate. Weak lensing depends on extremely precise shape measurement, careful knowledge of the telescope optics, and accurate estimation of galaxy distances. Galaxy clustering depends on uniform selection of sources, good control of survey completeness, and reliable three-dimensional placement of galaxies. The relation between galaxies and total matter must be understood statistically rather than assumed to be exact. Foreground contamination, detector effects, image blending, and calibration drift can all introduce false patterns if they are not managed carefully. For this reason, modern cosmology does not treat its largest surveys as simple collections of pictures. They are treated as precision experiments in which systematic error, meaning a bias that pushes measurements consistently in one direction, is often as important as random noise. Euclid therefore tests not only cosmological theory, but observational discipline itself. Before any tension with the standard model is taken seriously, astronomers ask whether the signal might arise from shape bias, photometric error, incomplete masking of bright stars, imperfect modelling of intrinsic galaxy alignments, or uncertainties in the distribution of source redshifts. This caution is not a weakness. It is part of the strength of the field. Claims about the deepest workings of the universe are made only after more ordinary explanations are examined and, where possible, removed. Existing cosmology already provides both reassurance and motive for this effort. The Standard Model has described a remarkable range of observations well, from the cosmic microwave background to large galaxy surveys and supernova distance measurements. At the same time, some modest tensions have appeared in recent years between different measurements of cosmic parameters. In some analyses, the amount of late-time clustering inferred from weak lensing surveys has appeared slightly lower than the value expected from the early universe picture. In another long-running issue, different methods of measuring the present expansion rate have not always agreed perfectly. These discrepancies do not yet overturn the Standard Model, and their causes remain uncertain. They may reflect hidden systematics, incomplete astrophysical modelling, statistical fluctuation, or signs of new physics. Euclid is important precisely because it can help distinguish among these possibilities with broader and more internally consistent data. The early Euclid results already show that the mission is capable of the required kind of work. The first data releases demonstrate image quality, wide mosaic construction, deep field coverage, strong lens discovery, galaxy clustering potential, and the first large-scale matter mapping from weak lensing. These are not final answers to the dark energy problem. They are the opening proof that the survey can build the measurement framework needed for those answers. Observations indicate strong promise, while it remains uncertain how far future full survey analyses will shift the present balance among cosmological interpretations. In this 14th region of the script, uncertainty becomes a disciplined part of knowledge rather than a failure of it. Euclid does not simply search for surprise. It tests whether the standard description of the universe continues to hold when the sky is mapped with greater depth, width, and precision. If the measurements align well, confidence in the current framework grows. If they diverge in persistent and well-tested ways, then some deeper revision may be required. Either outcome is informative, because both refine the account of what the cosmos is and how it behaves. So the path inward arrives at a place where observation and theory face one another directly. The visible galaxies, the weakly bent light, the hidden mass field, the growth of structure, and the geometry of expansion are no longer separate topics. They become mutual checks inside one cosmic test. Euclid's great work at this layer is to make those checks broad enough, precise enough, and interlocked enough that the missing parts of the universe can be judged with greater confidence than before. At the innermost layer of this subject lies a problem of accounting. It is not a ledger kept in ink, but a ledger built from light, gravity, geometry, and time. The question is no longer simply where galaxies are found, how clusters gather, how light bends, or how cosmic structure grows. The question is how all the known measurements fit into one statement of what the universe contains and how it behaves. In this deepest region, the idea that part of the universe is missing becomes less a dramatic image and more a precise confession of incomplete knowledge. The visible cosmos is rich and orderly enough to study in great depth, yet when its contents are measured against the behavior of the whole, the sum remains unfinished. Ordinary perception begins from the luminous world. Stars burn, galaxies shine, gas clouds glow or absorb, dust dims and reddens the light passing through it. These are the familiar ways matter enters observation. Even when the scales become immense, the principle feels intuitive. What exists leaves some visible mark. Modern cosmology breaks that expectation without abandoning observation. It shows that the universe can be known through effects that do not resemble ordinary appearance. Matter can reveal itself through the bending of background light. Expansion can reveal itself through the changing scale of distant structure. Thin ionized gas can reveal itself through faint absorption or the delayed passage of radio bursts. The deepest accounting therefore depends on a broader definition of evidence. The universe does not need to shine in order to be counted. Once evidence is broadened in this way, three different kinds of incompleteness stand out. There is the incompleteness of ordinary matter, where atoms expected from the young universe are difficult to find in the later one because they reside in extended halos and tenuous intergalactic gas. There is the incompleteness of gravitating matter, where the total mass required by lensing, clustering, and dynamics exceeds the ordinary atomic matter that observations can inventory. And there is the incompleteness of cosmic driving terms, where the large-scale expansion of the universe accelerates in a way not explained by matter alone. Each of these belongs to a different depth of the cosmic ledger. One concerns where familiar matter resides. One concerns the presence of additional matter unlike familiar atoms. One concerns the background evolution of space-time itself. This distinction matters because the word missing can mislead. It can suggest disappearance, absence from reality, or a gap torn into the fabric of the cosmos. The evidence does not point that way. The universe is not missing pieces in the sense of broken fragments. It is missing from human account. It is missing from the inventory that light alone would provide. It is missing from older intuitions about what counts as physical presence. The ledger is incomplete not because the cosmos has failed to keep itself whole, but because observation reaches its limits and must be extended by inference. What appears absent in one method may appear clearly in another. The missing part is often not gone. It is merely withheld from the most direct mode of seeing. Euclid belongs precisely at this point where seeing becomes inference without losing rigor. Its images are beautiful, but beauty is not the mission's final purpose. The survey is designed to weigh the visible universe against the hidden gravitational field that shapes it. It gathers the distribution of galaxies, the small distortions in their shapes, the statistical ruler left from the early plasma, the growth of structure across time, and the broad map of hidden matter. None of these by itself closes the cosmic account. Together they narrow the space of possible explanations. They do not yet remove uncertainty, but they make uncertainty more exact. A vague mystery becomes a measured one. This is one of the quiet achievements of precision cosmology. It replaces broad astonishment with structured ignorance. There remains much that is unknown, but the unknown no longer floats without form. Dark matter is not merely a name for anything puzzling in the sky. It is the term used for a gravitating component whose large-scale effects are repeatedly measured and whose detailed nature remains uncertain. Dark energy is not merely a poetic label for emptiness. It is the name given to the still unexplained cause of the observed late-time acceleration, constrained by multiple lines of evidence and still open to refinement or reinterpretation. Missing baryons are not lost in a careless sense. They are ordinary matter distributed in diffuse phases that require difficult measurements to detect. The ledger grows more complete as the unknowns become more sharply defined. At the same time, this deeper accounting imposes humility. The visible universe is not false. It is not an illusion to be discarded in favor of hidden components. The stars, galaxies, and gas clouds remain real and central. They are the places where chemistry becomes complex, where heavy elements are forged, where planets form, and where living observers arise. But they occupy only a minority share of the total cosmic content, and reveal only part of the governing structure. Human attention begins with light, because that is what human senses inherit most naturally. Cosmology teaches that light is an entry point, not a completed summary. In this 15th region, the title of a missing universe settles into its most careful meaning. What is missing is not a lost territory beyond the edge of a map. It is the hidden share within the mapped territory itself. It is the mass not luminous enough to see directly, the ordinary matter too diffuse to count easily, and the cosmic influence that drives accelerated expansion without presenting a visible face. The universe is fuller than its bright layer suggests, and its behavior is deeper than any inventory of glowing matter can explain on its own. So the inward path comes to rest not at an object, a field, or a mechanism, but at a balance sheet of reality. On one side lies everything that shines or can be imaged in familiar ways. On the other side lie the inferred components, the diffuse reservoirs, the altered paths of light, the measured geometry of expansion, and the hidden causes still under investigation. Euclid stands among the instruments that help bring those sides into closer agreement. It does not end the mystery, it makes the mystery measurable, and in that measured incompleteness, the modern picture of the universe becomes both more restrained and more profound, not empty where it looks dark, not simple where it looks clear, and not finished where the visible account seems complete. The account now grows quiet. The visible sky remains what it always is, a spread of light across darkness, filled with galaxies whose radiance travels for immense spans before reaching a detector or an eye. Yet after the long inward journey through surveys, structures, lensing, hidden mass, diffuse gas, and cosmic expansion, that familiar sky no longer appears self-explanatory. It appears as the bright surface of a deeper order. Euclid moves through that surface with patience. It does not tear away a veil in one sudden act. It measures. It compares. It gathers faint signals across broad regions and long ages. In doing so, it shows that the universe can be richer than sight first suggests without becoming less real or less orderly. The darkness between galaxies is not merely blankness. The great web is not merely a pattern of shining islands. The cosmic story is written partly in what glows, partly in what bends light, partly in what drifts thinly through the spaces between, and partly in the changing scale of space itself. What remains uncertain also finds its place. Observations indicate hidden mass. Observations indicate accelerated expansion. Observations increasingly recover the ordinary matter once missing from easier inventories, yet the deepest causes remain under study, and the full account is still being assembled. This uncertainty does not weaken the picture, it gives it honest boundaries. So the universe rests here as something neither empty nor fully disclosed. It is a cosmos in which light reveals much, but not all. Its visible forms remain beautiful and measurable. Its unseen parts remain active and consequential. Its largest behavior still invites careful thought. Euclid adds to this understanding not by closing every question, but by making the hidden share of reality harder to ignore and easier to trace. In that steady work, the missing part of the universe becomes less a void of ignorance and more a quiet map of what still waits to be understood.